So, we will continue our study of groups. A group is basically an algebraic structure. So, we denote it by G star. So, it is two components. The first is a set and the second object is a binary relation, a binary function from G cross G to G. So, it takes two elements, combines and gives an element as a set. Okay. So, that makes it a valid binary operation, and this binary operation should have certain properties. The first property was it should be associative. And the second requirement is there should be an identity and the third property was that every element should have an inverse. If these three properties are met for a binary operation on G, then we say that G together with the binary operation is a group. The examples that we have seen, like one of the examples that we saw, we can describe it by its multiplication table. So, when we specify the binary operation, we basically need to tell for each pair of elements what is the result of combining them. So, that can be given by a table. So, if we took G to be E, A, B and C, so this is the we want to describe here the group that we used to solve our puzzle on reachable configurations on a solitaire board. The group can be described as E is the identity and the others were the non-identity elements. E multiplied by E or E combined with E gives you E, and everything else, E combined with everything else leaves the other element unchanged. And any element when combined with itself gives identity. So, A with A is identity, B with B is identity, C with C is identity. And A combined with B gives C, A combined with C gives B. So, you need two elements combined, you get the resultant as a third element. You can complete the table, this is what we would get. Okay. So, this is the multiplication table. So, the table that we have written is the multiplication table. It is called multiplication table because we choose to describe this operation as, and usually the group operation is viewed as multiplication, though it could be very different from the arithmetic operation of multiplication. Now, this group has certain interesting properties. First is it is a finite group because there are only 4 elements in the group. So, in general a finite group means the size of G is finite. A group with finitely many elements in the set corresponding to it, that is called as a finite group. So, this is an example of a finite group. So far all the groups that we have seen are finite groups. Now, we could look at another property of this particular group, namely this is a commutative group. Okay, so, commutative group by definition what it means is, or A star B should be equal to B star A for all A B belonging to G. If this is the case, then it is called as a commutative group, which is clearly the case for this particular group that we have considered. In fact, all the groups that we have seen so far are finite groups. Let us see some examples. We will see that this algebraic structure that we defined is But there are many cases in mathematics where you come across objects which behave in this particular manner, many familiar examples. For example, if you take the set of integers, so this is a set of integers, they do form a group, but when we say group we need to mention the operation as well. So z under, so with plus, the usual arithmetic addition is a group. Okay, so we can check each and every property. Clearly you can add any two integer and the resultant is a new integer. So the operation, the binary operation plus is well defined on the set of integers. Further, we can verify that it is associative, and we claim that there is an identity element. That means there is an element x such that plus the identity will be x. Okay, so there is a special element e in the set of integers which makes this particular equation, let us call this equation 1, it makes equation 1 true. So if we can show that there is one element, then of course that element is going to be a unique element. So in particular here e will be 0. If you look at the 0 integer, that can act as the identity. Okay, so the identity property is checked. Further, we need to argue that for every element x, there exists y such that x combined with y. So here combination operation is y. So this should be equal to identity, which we discovered is 0. In particular, the integer minus x will do the task. And so you take x and add it to minus x, you are going to get 0. Okay. So every element has an inverse. Okay. So that was an easy example. Now not just this, if you look at the set of rational numbers, they also form a group under addition. If you look at the set of real numbers, they also form a group under addition. If you take the set of complex numbers, they also form a group under addition. So these are all examples of group under the usual arithmetic. Okay. But note that the addition operation is, although we refer to them as addition, the addition operation on integers is different from the addition operation on rational numbers, and it's again different from the addition on real numbers and on complex numbers, because if you think of them as operations, their domains are very different. Of course, when you restrict to the, because these are subsets of, there is some subset relationship between z, q, r and c. So if you restrict to, if you restrict the addition to just the set of rational numbers, then if you look at the addition on complex numbers and restrict that to just on rational numbers, then of course we are talking about the same operation. Okay. Now let us see some examples of certain algebraic operations which will not be, let us say, a group. For example, if we take the set of integers and if you look at multiplication, okay, this is a well defined binary operation. You can take any two integers and you can combine them. When you combine them, you will get an integer. Okay. So, and clearly that operation is associative. And is there an element which can act as identity? Of course there is. If you look at the element 1, so 1 multiplied by any element is going to give you the same element. Okay. Even if x was 0, 1 multiplied by 0 is going to be 0. Okay. So this is going to be trivially true. So 1 is the only element which will have this property. But now if you look at the inverse property which should be satisfied by every group, if you look at elements other than 1, or maybe even minus 1, if you look at let us say 5, okay, is there an element such that 5 times y is equal to 1? Okay. There are, for example, 1 by 5 can do the task, but still 1 by 5 is not an integer. So, this does not form a group under multiplication. So, z under multiplication is not a group, although this was a well defined operation. If you look at z under division, that also is not a group, because that is not division. You can't take two arbitrary integers and divide one by other. In particular, when the number by which you divide is 0, that is not a well defined operation, and therefore, that would not be a group. Now, if you look at this set of rational numbers, okay, you still have, you can look at all the rational numbers, you still have the associativity property, and 1 is going to serve as the inverse, 1 is going to serve as the identity, but all elements except except 0 has an inverse. Okay. So, this is almost a group, but not quite there because of 0. So, if you take Q and remove this element 0 from it, whatever you get is going to be a group under multiplication. Okay. But if you look at the same set, this is not going to be a group under addition. Okay. So, this is a group with respect to the operation multiply, whereas it is not a group with respect to say addition, because the inverse identity under addition was 0, and that is the element that we have removed from this set, and no other element can serve as the identity. You can look at rational this at real numbers, that is not going to be a group under multiplication, but if you remove 0, then we have a group under multiplication. Same with complex numbers, if you remove 0, they will form a group under multiplication. Okay. Now, we will, so these groups, all these groups that we have looked at here, they have this nice property that they are infinite groups. Okay. Z, Q, R and C, they are all infinite groups. So, we have seen examples of groups which are finite and infinite, and these groups are all, both the finite groups that we have considered and the infinite groups that we have considered are all commutative groups. We will later on see examples of non-commutative groups as well. Okay. Now, let us look at a special group which arises out of number theory. So, the operation is a very familiar operation, it almost mimics the addition. So, we will look at modulo n arithmetic. So, that this will be used to define the special groups that we are interested in. So, let us look at the set of integers, okay, and we are going to define a relationship between two integers, and we will say that A is related to B if A minus B is equal to k times n. Okay. So, if n divides A minus B, then we will say that A and B are related. So, we will start by fixing an n. So, if your n was 100, then 1 and 101 are related, because 1 minus 100 is minus 100, that is k times 100 for k equals minus 1. So, 201, 301, all these elements are related to each other, whereas 1 and 102 they are not related. Okay. So, this relation is a special relation, in the sense it is called as an equivalence relation. Okay. So, as you would have learned from your set theory lectures, an equivalence relation is a relation which is three properties. it should be reflexive, and it should be symmetric, and the relation should be transitive. Okay. So, if you look at the set of integers, this is your z. Clearly, for any n, this relation that we have considered is reflexive, because a is related to a for any a, okay, because a minus a is 0, that is going to be 0 times n, and it is symmetric. If b is related to a, this would imply that a is related to b, because b minus a and a minus b, I mean if one of them is a multiple of n, the other is also, and it is transitive because a related to b and b related to c. This would mean that a is related to c. This can be seen by observing that if a is related to b, then a minus b is equal to k1n, and b minus c, if you look at it, that is going to be equal to k2n, and if you add these equations up, you will get a minus c is equal to k1 plus k2 times n. Okay. So, this modulo n arithmetic, if you, we have not really talked about modulo n arithmetic yet. If we look at this equivalence relation, if we look at the relation tilde, that is going to be an equivalence relation. And one thing that we know about equivalence relation is, if there is an equivalence relation, then that is going to split up the underlying set into different partitions. So, if this was your set Z, if you look at tilde, you will get all the, you can partition Z into some number of parts. Here we can more specifically state what are the parts. So, we will call them as 0 prime or 0 bar, 1 bar, 2 bar up to n minus 1 bar. Okay. Where 0 bar or let us say a bar consists of all elements x such that x is related to a. Okay. If you take all the elements related to any particular element, that forms one particular equivalence class, and here therefore, there can be only n minus 1 equivalence classes. Any other element has to be, when you take any arbitrary element alpha, it has to be related to one of these elements 0 bar, 0, 1, 2 up to n minus 1, and therefore, must fall in one of these equivalence classes. So, here we started off with Z, and by looking at this equivalence relation, we have partitioned Z into a finite number of equivalence classes. So, for any particular element I, if you look at I mod n, that is the remainder that you get when I is divided by n, that is going to be the equivalence class containing, so if you look at that number you can think of as a representative element of the equivalence class containing I. Okay, so these are our classes 0, 1. Okay. So, although we are writing, so let us say our n, think of it as 100, although we say that our classes are 1 bar, 2 bar up to 99 bar, we could say that 101 bar, this can be defined as the equivalence class containing 101, and that is going to be equal to 1 bar. Okay. So, now what we have is a partition into equivalence classes. Let us see if we can do arithmetic with these classes, which will mimic our normal arithmetic. Okay, so suppose, so I want to multiply two equivalence classes, does it make sense? And for example, what is going to be 1 bar into 3 bar. I could define this to be equal to 1, or let us say 5 into, okay. So, 15 bar into 13 bar, I could define that as 15 into 13 the whole bar. Okay. Now, this is going to be a valid definition only if I take other elements, let us say 115, which is in the same equivalence class, and multiply it into, let us say, 213 bar. By definition, this should have been 115 into 213 the whole bar, but since these classes are the same, these classes also, the classes on the right hand side also must be same. In other words, 15 into 13 the whole bar should be equal to 115 into 213 the whole bar if this arithmetic is to make sense. You can easily verify that that is the case. That is the case in case of both addition and multiplication. Okay. So, we can say A bar into B bar is going to be equal to A into B the whole bar, okay, because A bar is going to be all those elements which leave a remainder A, and B bar is all those elements that leave a remainder B. Okay. So, A bar, you can think of A as, let us say, remainder A plus k times n, and B is equal to remainder B plus k1 k2 times n, and AB is going to be equal to remainder A, remainder B plus all the other terms are going to contain n in them. So, this is some expression alpha times n, and this is just, I mean, if you look at AB and consider the equivalence class of AB, that is going to be same as the equivalence class of RAB. Okay. So, the remainder that A leaves when you divide it by n alone is the alone determines the equivalence class containing A. Okay. So, you can work out the arithmetic and verify that the operation of addition and multiplication are indeed well defined. Okay. So, early in all our earlier examples, we started with an operation which is well defined, except in the case of division we had well defined operations of additions over integers, over complex numbers, over rationals and so on. But here we have a new set which consists of equivalence classes, and on these equivalence classes we have defined two operations, one of addition and one of multiplication. In fact, we have defined infinitely many operations, one for each number n. Okay. Fix a number n, if n equals 100, you have a particular split into equivalence classes. If n is 113, you have yet another split into equivalence classes. Okay. Once you fix the collection of sets or the equivalence classes, you can multiply them, you can add them in a certain way, and those operations make sense. They are valid binary operations on a finite set, because each of these equivalence classes, although they might be infinite, the number of equivalence classes is always going to be finite. Okay. If you are doing mod n arithmetic, if your equivalence relation is defined on, let us say, some number, finite number n, the number of equivalence classes that you would have is a finite number, and therefore, this is a finite set on which we are operating. So, we can ask ourselves this question: is this finite operation along with these equivalence classes a group? So, we will see that under addition they do form a group, but under multiplication they do not. Okay. But there is a way of extracting a group out of these operations for multiplication as well. We will see that in the remainder of this lecture. So, let us first see the easy part. So, we will first give some names to this. So, Z mod nz, this is a notation. When we write z slash nz, what we mean is this is defined as the equivalence classes arising out of the equivalence relation tilde. Okay. So, I am going to write tilde n because we say that A is related to B, A tilde n B if A minus B is a multiple of n. Okay. So, this is dependent on the particular n that you choose, and Z mod nz, that is how this is read. So, Z mod nz is going to be the equivalence classes arising out of this particular relation. Okay. And if we look at the addition operation of these classes, so Z mod nz forms a group under plus. Okay. So, this plus is not the usual addition of numbers, but this is the mod n addition. Okay. So, you add two equivalence classes, we add it in the way we had described earlier, and that is same as the modulo n addition. Okay. Why is it a group? We need to check first of all that this is a valid binary operation, that is something that we had seen earlier, and clearly it is associative, and the equivalence class corresponding to 0 will act as the identity, and for any element x, if you look at minus x, okay, or the equivalence class containing minus x, that will be the inverse. Okay. So, we can easily verify inverse property also. So, once you have a finite collection with the property of with the operation being associative and identity and inverse is being present, we know that that forms a finite group. Now, let us look at Z mod nz, the same set under multiplication. Okay. So, in this case, if we look at let us say, so let us take an example. If you take n is equal to 10, then our equivalence classes are 0, 1, 2 up to 9. Okay. So, 0 bar, 1 bar, 2 bar up to 9 bar. So, 0 bar consists of all the numbers which are multiples of 0, 1 consists of all the numbers which are 1 more than a multiple of, sorry, 0 bar consists of all the multiples of 10, 1 bar consists of numbers which are 1 more than a multiple of 10, so on. So, 0 bar is 0 plus or minus 10 plus or minus 20 and so on. 1 bar is equal to 0 plus 1 plus or minus 10 plus 1 plus or minus 20 plus 1 and so on. And so, these are your different equivalence classes. Now, if we look at 2 bar, that is one of the elements. Is there an element x such that 2 bar multiplied by x will give you identity? Okay. Clearly, we need to check with only elements 1 to 9, but one thing that we can observe is when you take 2 bar and multiply it with x and take the whole complement and look at the equivalence class containing 2x. So, this is equal to 2x bar. Okay. 2x is always going to be an even number, and here 1 bar we can check that if there is an identity, then 1 has to be that identity. Identity has to be unique and it has to be 1. Okay. And 2 times x bar is going to consist of only even numbers, and therefore, this cannot be equal to 1 bar. Okay. So, clearly this set of numbers cannot form a group, at least when n is equal to 10. So, in general it cannot be a group under multiplication operation. Is there some way to extract out a subset of these such that they form a group? So, now we will stop pretending that these equivalence classes are going to be sets. Instead, we will just work with the representative elements. Okay, that is much more convenient than just, let us say, thinking of these 1 bar, 2 bar and so on. We will just replace with numbers 0, 1, 2 up to 9, or when we are looking at the equivalence class corresponding to n, I mean we are going to, when we are looking at modern arithmetic, we will think of the equivalence classes denoted by numbers 1 to 0 to n minus 1. Okay. We will not put the bar above it and pretend that it is a set or it is an equivalence class. Instead, whatever we do with the numbers themselves can be restated in the language of combining the sets via the equivalence relation. Okay. So, if we take these numbers 0 to n minus 1, can we somehow make this a group under multiplication? Okay, maybe the element 0 is going to be the troublemaker. Okay. So, let us first work out an example involving when n is equal to 10. Okay. So, if you have 0, then clearly the multiplicative inverse is going to be difficult to come by, okay, because any element multiplied by 0 is going to, or a multiple of 10. Okay. So, x into 0 will always be equal to 0. Okay. It will never give you 1. So, 0 cannot anyway have an inverse. What are the other elements which may not have an inverse? So, we will try to remove the elements which does not have an inverse and look at the remaining set and hope that that will do the trick. Here at least the evenness is causing trouble. So, let us say we remove all the even numbers, okay, then we will get 1, 3, 5, 7, 9. Okay. But 5 is also a troublemaker here in the sense 5 times x is going to be, and this is always going to be a multiple of 5. So, you will never get 1. Okay. So, maybe we will remove 5 as well and we will look at 1, 3, 7, 9. Okay. So, now if we just have these 4 elements, let us try and see, let us try and write the multiplication table corresponding to it. Okay. So, our elements are 1, 3, 7 and 9, 1, 3, 7 and 9. 1 into 1 is 1, 1 into 3 is 3, 1 into 7 is 7, 1 into 9 is 9. Okay, this is going to be a commutative group. So, we need to look at only half the elements, almost half the element. 3 into 3 is 9, 7 into 7 is 49, that is also going to be 9, 9 into 9 is going to be 81. So, this almost looked like our EABC, but that is not the case because 3 times 3 is not going to be 1, okay, and 7 times 3 is going to be 1 because 7 times 3 is 21, which is 1 mod 10, and 7 times 9 is going to be 3, 63. 3 times 7 is 1, 3 times 9 is 7. We can fill this up. Okay, so, we get a multiplication table, and from this table we can infer that all the properties that was required of the group is basically true. So, this has an identity which is 1 and inverse is also there. Okay. So, namely the inverse of 1 is itself, of 3 is going to be 3 into 7 is 1. So, inverse of 3 is 7, inverse of 7 is going to be 3, inverse of 9 is going to be itself. Okay. So, once we have verified the identity and inverse, associativity comes for free and we have checked this is a valid operation. Therefore, these elements form a group. Okay. So, this is denoted by Z 10 because we were doing mod 10 operations 10Z. Okay. The reason why we are writing it in this particular form Z divided by 10Z or Z mod 10Z, that will become clear in one of the later classes, but right now we will just view this as a notation. So, we are not taking all the elements. So, when we write multiplication here, this is what the although we are writing as Z divided by 10Z into with the multiplication operation, this basically means we are considering elements 1, 3, 7 and 9. So, what is the natural generalization of this? If it is NZ, what does it mean? Which are the elements that stays, which are the elements which will go out? here at least in case of 10 we could extract a subset of elements which form a group amongst themselves. In case of general n, can we do this? We can do that, and therefore, when we write z n z star, this is the multiplicative group under mod n multiplication. Okay. So, what are the elements that goes into this? We will make it clear in a short while. Okay. You can try to guess what are all the elements that are going to be there in z divided by nz. It is going to have at most n minus 1 element, because 0 is automatically not going to be present there. So, the elements from 1 to n minus 1 could be present, and that is present in some special cases. Try and figure out what is a special case, but right now we will describe more precisely or more explicitly what are the elements there in z mod nz under multiplication. Okay. So, let us look at all the elements A which are less than n, and the GCD of A n is equal to 1. Okay. So, if you look at these collection, we will show that this does form group under multiplication. Okay. So, this look at this collection, we will prove that this forms a group under multiplication. Okay. But if we wanted to prove that z divided by nz is equal to this, we need to show that our process was look at all the elements in z divided by nz. There are at most n elements, 0 to n minus 1. From these, all the elements which could possibly not have inverses, we threw them out. Okay. And whatever remains, they will all have inverses, and that is precisely this collection. Okay. Why is this so? Okay. So, if you take any element, let us say if alpha belongs to z mod nz and GCD alpha n is not equal to 1. Okay. Then clearly, if you multiply, if you look at alpha x has a common factor with n, okay, because alpha has a common factor with n, alpha x will also have a common factor with n, and therefore, alpha x cannot be equal to 1 ever, okay, because if this was equal to 1 mod n, then alpha x minus 1 is equal to k times n. Alpha x has a factor, so this would mean alpha x minus k n is equal to 1, but alpha x has a factor with n. So, if you take the common factor d out, so d into alpha by d x minus k into n by d, this is equal to 1. So, this is some number which is greater than 1, and this is going to be an integer. So, how can we multiply two integers which are different from 1, and of which at least one of them is different from 1, and get 1. So, this is impossible, and therefore, all the elements which are outside the set that we have described here must be excluded. Okay. In other words, any element such that GCD a comma n is not equal to 1 cannot have multiplicative inverses. Okay, so that is one part. Now, we need to show that every element which satisfies the property that its GCD is 1, GCD with n is 1, they will have inverse. Okay, so, we will use the following lemma. Okay, if you look at a number, so GCD AB is the smallest positive number in the set alpha A plus beta B. Okay, so if you look at alpha A plus beta B for alpha beta belonging to integers and take all possibilities, you will get an infinite set. In that infinite set, the smallest positive number is equal to the GCD. We will not prove this statement. It can be easily proved from basic number theoretic facts, but this is the, so you can either treat this as the definition of GCD. Let us work out one example. If you look at, let us say, 12 and 15, okay, the numbers that you could form are, let's write few of them. 12 is possible, 24 is possible, 36, and the negative of this are all possible. Minus 12, minus 24, minus 36, 15, minus 15, 30, minus 30, all these numbers are possible. And this set has a nice property that, look at numbers of the form alpha A plus beta B. If you take two of them and add them, you still get another number in the collection, okay, for of course a different alpha and beta. Okay. So, minus 12 and 15, if you add up, you will get 3. So, 3 is also going to be an element in the set. Okay. And you can argue that 3 is going to be, there is going to be no other number smaller than 3 and strictly positive. Okay. So, at least in this case, you can easily verify that the GCD is in fact the smallest positive number that can be obtained as a linear combination of 12 and 15. Okay. So, we can use that fact that GCD AB, smallest positive number of the form alpha A plus beta B. So, if GCD AB is equal to D, then D can be written as alpha A plus beta B. So, from this fact, if GCD AN is equal to 1, this would imply that alpha A plus beta N is equal to 1 for some alpha beta belonging to integers. Okay. So, now if you look at this alpha, alpha is an integer, look at the equivalence class which contains alpha. So, if you look at alpha bar, when the representative element for that class is going to be the inverse for A, because that is clear from this equation. Alpha times A is equal to 1 minus beta n. Okay. So, alpha when multiplied by A gave you 1 mod n. So, if you look at this equation mod n, so alpha A is equal to 1 mod n. So, from this definition, it is straightforward that any element of the set defined in this particular manner must have a multiplicative inverse. Okay. So, we can, so if you look at this set, we can look for multiplicative inverses, we can look for associativity comes for free, and identity 1 is surely an element of this set because GCD 1n is of course 1, and therefore, this forms a group under multiplication. Okay. So, we have two new groups, in fact infinitely many new finite groups. So, this under addition mod n and Z under multiplication mod n. Okay. So, although the arithmetic is mod n, the sets are going to be different in both cases. In the first case, surely the set will contain 0 and it will contain all the other n minus 1 as well, n minus 1 elements as well. Whereas, if you consider the multiplicative group will have strictly less elements than n. If n is prime, then and only then Z and Z will have n minus 1 elements, because if n is prime, the numbers which are relatively prime to n, or the numbers which have GCD with n as 1, are all the numbers less than n except the 0. Okay. So this gives us many examples of finite groups. We will now see some other examples from the set of complex numbers. Okay. So let us look at the complex plane. So if you look at the complex plane, then each complex number can be thought of as, so let us say r e raised to I theta. Okay. So this is the angle theta and this distance is r. Now if you look at the roots of unity, okay, so complex numbers, if you remove the 0 complex number, that is of course going to be a group under multiplication. Let us look at another example. So let us look at the unit circle and let us look at, let us say, the n roots of unity. Okay. So let us say n is equal to 10. So consider the n roots of unity. So if the nth root is going to be, let us say, omega, you can check that the other roots are going to be omega square, omega cube and so on up to omega raised to n minus 1. Okay. So 1, omega, omega square, omega raised to n minus 1 are going to be the n roots of unity, where omega is e raised to I 2 pi by n, okay, where I is the where I is square root of minus 1. So now let us just focus on these numbers. Do they form a group? So of course we have to think about what is the operation. If you add two of them, if you take omega raised to 3, I mean let us say if n is 10, this multiplied by omega raised to 9, this is going to be omega raised to 12, it is going to be omega raised to 10 into omega square, and that is going to be just omega square. So here the multiplication is the complex multiplication restricted to these 10 numbers. So we are looking at these 10 numbers, omega, omega square up to omega raised to 9. You can check that these complex numbers could be multiplied as these could be multiplied as complex numbers, and the resultant is going to lie in the same collection. So we have a valid binary operation on the set of nth roots of unity, and that operation, because complex multiplication is associative, we have an associative operation. And you can verify that since 1 is there, there is a multiplicative identity, and also every element here can be inverted as well, and therefore these form a group under multiplication. Okay. The next example that so this is again a finite group which is a subgroup of an infinite group. If you look at matrices, if you look at the collection of all matrices, that is not going to be a group in general, because under matrix multiplication there are a lot of matrices which cannot be inverted. So if you look at invertible matrices, you can show that they also form a group under matrix multiplication. We will stop here for today and continue our discussion on groups in the next class.